Good afternoon, everyone. My name is Dale Brosius. I'm the Chief Commercialization Officer for IACMI, and welcome to the February 2025 edition of Innovation Insights. As I said, I am the Chief Commercialization Officer, and we do have a couple of great presentations for you today. Thanks all of you for joining. But before we get there, I just want to remind, there's a slide I put up every time, but ACME is centralized around the themes of convene, connect, and catalyze, bring people together, hook them up, and then make great things happen. And we do that through a lot of mechanisms, whether it's our members' meetings, funding mechanisms, networking facilities, the expertise that we bring, the working groups that we've created, and the workforce development aspects that we emphasize. If you are on this call or joining us today and you're not an ACME member and have an interest, go here to www.acme.org/members and fill out the form, and we will be right back to you to discuss membership and if you have any questions, answer those. Just to point out a couple of events. One, make sure everybody saves the date for our members meeting. You do have to be a member to attend this for free. It is a benefit of membership, the free attendance to the ACME members meeting this year in Dayton. 3 days of very, very active events that occur there. We're pleased that this is being done in partnership with our friends from Jobs Ohio, who have invested a long time in IACME's success and are also supporting us with some of our activities at the members meeting. Next week, we have an open house at University of Tennessee Research Park at the Innovation South facility, which was recently constructed and turned over to us in October. It includes the fibers and composites laboratories of Professor Uday Vaidya. So there's lots of scale-up equipment in there, some very interesting things. And we will be having an open house next Wednesday afternoon. So if you're interested in that, I don't have the link here, but Kim can put that link into the chat. And we can, if you want to sign up to join us there. It's also a location of ACME's headquarters now. We've recently moved into those. In a few weeks, the first week of March, we will be at JEC World 2025 in Paris. We have a booth in the U.S. Pavilion, so come see us there. And we would love to discuss how we can help grow your business and engage further. So we'll be in Hall 6, stand Q32. And before we get started with today's Innovation Insights, I'll just note that all of the previous webinars are archived on our website, iacme.org, under Innovation or under Events and Innovation Insights. So you can go back and capture these. We're recording this one today, and it will be there as well. If for some reason you have a colleague that couldn't make it and you saw something you really liked, or you want to just go back and review something that you saw. And we will be sending out a link to that video a little bit later in the week. We do have some upcoming ones planned throughout the year. The only one we don't do Innovation Insights is June, when we have our members meeting. But the next three are scheduled on Mondays over the next 3 months in March, April, and May. And we do have available presenter slots available for all of those, but they're closing fast. So if you are a member of IACME, you do have to be a member of IACME to present. You don't have to be a member of IACME to attend. So today, before I'm about to bring on our first presenters, but we've got great presenters here from Bostik/Arkema, Mike Stanton, Senior Account Manager, and Michael Barker, Research Fellow and R&D Technical Manager from Bostik, and some pretty cool technologies that they bring into market, and especially in light of the growth in thermoplastic composites in our industry. So, and then we'll follow that with John Unser from Composite Applications Group. We did have a third speaker lined up. Unfortunately, we'll have to postpone that. It was from one of the national labs, and with all the transition going on in the country right now with the new administration, they've had to put a pause on those kind of public presentations for a moment, but we'll certainly get them on as soon as that opens up again. So Michael and Mike, if you want to share your slides, and we'll get started with you. One thing I will mention while they're bringing theirs up is that we do, if you have any questions, put them in the chat or put them into the Q&A panel, and we will get to as many of those as we can. Gentlemen?
Okay.
What we're seeing now is an email. Is your email? You need to change which, either go down to the tab and change what you're sharing.
There we go. Can you see the screen now with the presentation?
Not yet.
Okay. We just put it on.
No,
I have more than one screen. If you have more than one screen open, you need to switch it
Switch
to the other
screens.
screen because we're seeing
Switch
your
screens.
emails right now. Thanks.
Yeah, she just mentioned got more than one screen up. We might switch it.
A lot of times at the top of the presentation, you'll see switch view or something like that.
Yeah. It says your screen sharing is paused.
Mike and Michael, if you'd like, I can share the slides from here.
Yeah, why don't we do that? Why don't you
Okay.
just go ahead and you'll
Hey, give me a second to
okay.
to get those. Could you please stop sharing? Thank you.
Okay. Yeah, she's gonna go ahead and put the slides up.
Are you able to see them now?
Oh. Okay. We're looking at Michael's now, so apparently you got it fixed.
Okay.
And so,
Well, you got to have a
All
little
right.
excitement in the beginning of a presentation
Yeah,
to make
right.
it go smooth. So,
all right. So gentlemen,
all right.
Take it away.
Okay, thank you. Well, we appreciate everybody joining us today for the presentation, and real excited to be able to present this new technology. My name's Mike Stanton, and I'm a senior account manager with the Bostik Adhesive Company. We got Michael Barker, who's our R&D technical manager, and we're going to be presenting the new technology today. Our topic is the polyolefin composite bonding. This is our low modulus adhesive that's used for bonding thermoplastics, also other applications as well. But we'll be reviewing that. One of the key things with this technology is a lot of changes going on in the market right now with people going from structural composites to thermoplastics. And so what we're going to be presenting is some of the market drivers that are initiating the change, what the materials are themselves as far as mixed bonding of composites. And then we're going to be going into the technical solutions. And that's basically the low modulus adhesive systems that we're going to be presenting today, as well as some supporting data for it. And then we'll be summarizing with more information about the new adhesive technology. A little bit of background. We are Bostik Adhesives, but if you look at the history of our business unit, we were with Ashland for many years. We were part of the structural polymers and adhesives division, and even going back even further, the plier grip technology that we'll be talking about today. This was a technology that was bought by Ashland back in 1984, and we bought it from the Goodyear company. And Goodyear had developed it previously to that and introduced it out to the market for structural applications in the transportation industry, primarily for heavy trucks. But this adhesive has been in use for over 55 years, and it's been used for many different applications. And the plant that we make these products at is in Ashland, Ohio. And that's a plant site that's part of our business unit that we own. We do have backup manufacturing capabilities. That's in Columbus, Ohio. And then we also manufacture these technologies at our facility that's over in Europe. It's at Kidderminster, which is in Great Britain. In 2014, one of the things that they did over there was they built a brand new lab with full R&D capabilities, and so they can support the European customers very well. Now here in the United States, our tech center is located in Dublin, and that's a picture of our R&D facility right there. But we're set up to do analytical work. We're set up to do lab testing for doing bond screens. And so we're fully capable to run just about every test that's out there for looking at the integrity of the bond performance. As I'd mentioned, we were sold by Ashland in 2002 to Arkema, and we were rolled into their adhesives division, which is called Bostik Adhesives. So there's a lot of capabilities and a lot of different synergies from that acquisition, and we're up and running right now and doing and moving forward with this integration. Below is a picture of all the different OEM approvals that we have. We have many more besides that, but those are some of the customers that we currently do business with the Ply Group adhesives. Okay, what I'm going to do now is turn this over to Mike Barker, and he's going to do the technical side.
Good morning, good afternoon. This is Michael Barker, and it's a pleasure to be here. So this slide basically is reviewing the status of our in-house laboratory, and some of the highlights include, we are set up here to run every OEM specification in the world, and we've got all the necessary equipment to R&D, new adhesives, including, bonders, flame treaters, plasma treaters, contact angle equipment, bond line read through. And so we've got a world-class facility here, and it's staffed by world-class personnel. So I want to jump into the meat of the presentation here. And fundamentally, there's some shifting paradigms in the automotive and heavy truck industry. And I think everybody's aware there's been a huge push to lightweight vehicles and heavy trucks to improve fuel efficiency and reduce carbon emissions. And of late, the focus has gone through low density sheet molding compound, carbon fiber based composites. And right now, the fish in the bowl that's getting the most attention from our perspective is thermoplastic olefins, or TPO. And the thermoplastic, it comes in a glass-filled composite version, which we'll summarize as GFPP. And the application that we're going to talk about today is TPO, which will be thermoplastic olefin without glass, bonding to glass-filled polypropylene with glass. And some of the key things that stand out when you're trying to do those type of assemblies is that you have a mixed CLTE, coefficient of linear thermal expansion, and also you can have issues with bond line read through, and of course fatigue. So let me jump into it here a little bit. Right now we have listed a table here of the two different substrates that I'm going to talk about. There's a glass-filled polypropylene and the thermoplastic olefin. And really the things that I wanted to point out here, we've got the star on it here, and we're talking with the glass-filled polypropylene, a CLTE of about 71, and then with the without the glass, a CLTE of about 334. And so what this is doing is it's setting up a huge differential with the expansion and contraction of the two different substrates. And what happens when that occurs? When the temperature changes, and we can use an example of having cool temperatures in the morning and higher temperatures in the midday, and then cooling down again in the evening, the two substrates will expand and contract at different rates. And that puts a lot of stress on the adhesive. And that's really what we're going to focus on today, is how do we deal with that stress, number one, and then number two, how are we going to get the adhesive to bond to a polyolefin which is a very hydrophobic type of substrate. So those are our objectives, and these are our solutions. So our approach, we took 3 different approaches. One, we wanted to understand how the constitutive properties of the adhesive would impact the adhesion and the durability. 2, we used finite element analysis to model the in-service stress. And of course, then within that model, we could change the properties of the adhesive. And the outcome of that was that the Young's modulus of the adhesive and the CLTE of the adhesive were most impactful. And then the third area was to understand the chemistry of the surface of the substrate and how the adhesive would interact with that. In that regards, we used X-ray photoelectron spectroscopy to not only understand the surface chemistry, but how that could, as I pointed out, interact with an isocyanate-based polyurethane. So we'll take a quick look at the surface analysis. And why is this important? And right here in the middle of the slide, I'm showing contact angles of various different thermoplastics. And up on the top, of course, would be Teflon, and that's extremely hydrophobic. And you put a bead of water on there and it's going to bead right up. And then down at the bottom, as we move from the top of this list down to the bottom, you're getting more and more oxygen blended into the structure, and it becomes more hydrophilic, and then water would want to wet that out easier. Well, when we're talking about polypropylene or polyethylene, it's way up here at the top. So there's a couple of things we can do to introduce oxygen into the surface of the polyolefin. One of them is flame treatment. The other is a plasma treatment. And the literature is very clear on what's happening here. The flame or the plasma breaks the carbon-carbon bonds on the surface of the substrate and inserts oxygen. And that's a very key takeaway. And it's the oxygen introduction into the surface which allows a polyurethane adhesive to bond to it. So if we take a look at the XPS data, and I promise I won't go through this entire table here, but right up here on the top line where it says PP control, I'll just move over to the 4th column over for oxygen. And you can see the control has very little oxygen. And then if you drop down to the 3rd row for polypropylene with plasma treatment, that amount of oxygen jumps up to 10. And we also did the same with flame treatment. And so you can see adding that plasma or the flame treatment puts oxygen on the surface of the substrate. And then down below here, it basically can tell you what structural array those elements are in. And that varies from an alcohol to an epoxide, carbonyl, and carboxyl. So the takeaway from this is you can use either the flame or the plasma to introduce the oxygen into the surface of the polyolefin. That creates a higher energy surface, which then allows the polyurethane adhesive to wet it out. And so what we have done is we've developed some new adhesive technology. This is called PlyoGrip 200-208, and it is a 2-component polyurethane. And I'm showing here the diol reacting with an isocyanate to create a polyurethane. Very fundamental reaction, and one that we're going to leverage. So what we've done here is we've got 2 examples. We've got a high modulus adhesive, which we're going to call the control. And then we've got the low modulus adhesive, the PlyoGrip 200. And a couple of areas that I wanted to focus on is the modulus, 484 for the control, megapascals, and only 5 for the low modulus adhesive. Huge difference there. Percent elongation for the control is 34. Elongation on the PlyoGrip 200 is 280. Those 2 constitutive properties right there are going to come to play and help us to get a more durable bond on the surface of the polyolefin. And so our first example here is we're going to take these substrates. We're going to bond TPO, which has got no glass in it, to glass-filled polypropylene, and we're going to vary the bond gap. And so when we vary the bond gap, where they're going to pull a lap shear at -30, at 22 and 82 centigrade, and compare the strength values of the control, which is the high modulus, to the low modulus adhesive. And without going into a lot of detail here, the numbers are very similar. So when we saw that, this did not align with the FEA model that we had generated. So we scratched our head and said, so what's the advantage of a low modulus adhesive in these applications? So we put together an example. And in this case, we're using an example of a TPO bonded to a glass-filled tailgate for an SUV. And we used the dimensions 152 centimeters square. And we ran that through a basic engineering program or equation using extreme temperatures, cold versus hot. And we determined that those two substrates, when the temperature varies over the range given, can vary up to 4.2 millimeters. Now, if you hold your fingers up and say, well, gosh, 4.2 millimeters isn't very much, or is it? So that's a number that we're going to play with right there, that 4.2 millimeters. So what we did is we put together a series of lap shear, same substrates, always working with the TPO bonded to glass-filled polypropylene. And in this case, we're using a 0.76 millimeter bond gap, and that's about 30 thousandths of an inch. And in this graph, you can see that there are two lines. The first is the control, or the high modulus adhesive. The second is the low modulus adhesive. And a couple of things can be taken away from this graph. The first, the high modulus adhesive and the low modulus adhesive failed at roughly the same strength. Well, that's pretty much what we saw on the previous two slides. But when we take that 4.2 millimeters that we calculated from that engineering equation, and we plot that on here as well for stress strain, we see that at 4.2 millimeters, the high modulus adhesive had already broken. So there is no way this high modulus adhesive would have allowed this bond to stay true when it expanded, when the assembly expanded differentially 4.2 millimeters. So that is fundamentally the advantage of the low modulus adhesive. It is able to elongate and accommodate the differential and expansion of the assembly. So we took that a little bit further, and we took those same adhesives, the control on the left, and we varied the bond gap. So we were at 0.76, 1.53, and 6 millimeters. And as we tested them, you can see that they all failed at approximately the same extension. Now, the strength values differ, but as we increased the bond gap, the strength came down. But they all failed at the same extension. And why is that? Because they all broke the composite substrate. Now, over on the right, we did the same thing with the low modulus adhesive, and we started testing them. Now, we're varying the bond gap as previous, but now as the strength is coming down, the elongation is going up. So in all cases, they far and exceed the 4.2 millimeters worst case expansion contraction of that assembly. And that in itself is the true advantage of the low modulus adhesive. And so how's that going to play out? It's going to build a more robust assembly, and it's going to greatly reduce the potential for bond line read-through, which in itself allows the molder to bring out a thinner gauge substrate. So then what other advantages might be created with this low modulus adhesive? Well, as you know, as the expansion and contraction, the stress that is generated on the bond line from that part moving and contracting with the temperature, it is generating a certain strain on the bond line. With the low modulus adhesive, that strain is actually, the stress on that bond line will actually be less. And as a result of a lower strain on the bond line, it translates into a higher fatigue resistance for the assembly. And that's a pretty significant point to take away. Even though the strength is less with the low modulus adhesive, and I'll back up to that picture. You can see that the stress, in this case, we're going to lower or higher and higher bond gap. Even though the strength is coming down, you're not going to reach the point of deformation, the catastrophic failure point of the low modulus adhesive when it's driven by the expansion contraction of the assembly. Okay, so that brings us to the wrap-up slide here. So we've got this Plyo Grip 200 low modulus 2-component polyurethane adhesive, and these are the attributes that make it unique. It's been set up to bond these low energy surfaces without a primer, and this will minimize the amount of economies that you need to put into creating an assembly. It does need to be flame treated or plasma treated, but all of the commercial polyolefins today require some level of surface treatment, but we do not require a primer. It's got a low modulus and a high elongation, which will then account for the dissimilar CLTEs of the substrate. It's got excellent adhesion to not only the TPO and the glass-filled polypro, but also to SMC, E-coat, polycarbonate, aluminum, and glass. So it's quite a robust adhesive. It is now commercial. We have a customer on the West Coast that is using this to build assemblies. So it's commercial. It's got an open time or a working time of 3 to 15 minutes, and that can be varied. And this adhesive can be cured at room temperature or heat cured. And then finally, this is a gravity feed type adhesive. So when you're looking at investing in dispense equipment, the adhesive does not need to be pushed out of a pail or a drum. It just needs to be tipped over and attach a line to feed the gerotor type of pumps. So that minimizes the investment in setting up the process. So that's where we're at today. And if you have any questions, we're certainly willing to cover them for you.
Thanks, Mike. Thanks, Michael. I want to remind people, if you do have some questions, put them in the chat or in the Q&A panel. In fact, one just came up in Q&A panel. So the question is, how do engineers model a lower modulus adhesive with differing bond gaps? So do you have recommendations to bring to OEMs for design guidelines?
Yeah, so I would recommend getting the exact substrates, and if you want us to be involved in that, send them to us. We can run that bond gap study and collect the Instron data or that tensile data, and then that information can be fed into a material card, which will then take into account the varying strengths and performance as the bond gap is varying.
Great. Yeah, I was going to ask you the same thing. I saw that you tested anywhere from 0.76 to 6.1, but where have you settled on? Let's just say, let's take that liftgate example where you have the TPO outer, the glass reinforced polypropylene inner. What is a typical bond gap there?
So a typical bond gap for bonding polyolefins is in the range of 0.76 millimeters or 30,000ths of an inch. And that's fairly common in the industry. And that allows for some level of variation in the molded panel to allow the adhesive to take up any changes in topography of the panel, but 0.76 millimeters is quite common.
Okay, so it was toward that lower end.
Yes.
That you tested. Okay, all right. And you mentioned heat cure or room temp cure, both. What temperature do you have to go to heat cure? Because certainly that in and of itself would apply a little bit of stress.
Yes, so
differential
right now
release
we're
rates.
curing this at 82 centigrade for 60 seconds. And then while it's still in the fixture, we turn the heat off and allow it to sit for another 30 seconds. So I have about a 90-second cycle time using 82 centigrade, or that's 180 Fahrenheit. So we're
Okay.
not taking this, we're getting a lot of change, dimensional change in the assembly.
Okay. So how do you control the bond gap? Are you putting any beads in, or is that just fixture?
Well, yeah, how do we control the bond gap? So in our laboratory, we use glass beads. In an assembly, in production, they would mold bond standoffs right
Sure.
into the die itself. So when the assembly comes out, those standoffs are already in there.
Sure. Okay. What's the mix ratio of two components? Is it
It's a 1-to-1 system, which is
Okay.
very common in the industry.
Right.
And yeah, so
Good. All right. So if we've gotten to all the questions that I had, and well, I could have more, but yeah, we need to get to our next speaker. But if folks still have any, put them in the chat or the Q&A, and we'll have Mike and Michael monitor that through the rest of the session, and they can answer them directly there. So appreciate it.
okay.
Thanks,
Thank you,
guys.
everyone.
Michael, yeah, wish we had this this adhesive back in the early 2000s when we were developing that first Corvette carbon fiber hood.
Well, actually, we supplied
Yeah, we
adhesive
did.
for that carbon fiber hood on the
Yeah.
Corvette.
We
If you're
did.
not aware
So,
of that. So yes.
if you remember, we chased bond line read through for a long time on that.
Oh, yes. No,
Yeah.
that is absolutely true. But
Right.
we did solve the issues.
We did. Yes.
All right. Thanks, everyone.
All right. Thank you. So if you stop sharing, and I'll ask John Unser, who's the Vice President and Program Manager for Composite Applications Group, to fire up his presentation, and we'll.
Can you guys see it?
Sure can, John. It's all yours.
Perfect.
Take it away.
Great. Hi, I'm John Unser. I am the VP of Program Management at Composites Application Group. I'm been in this wonderful industry for many, many years, and I have lots of different passions: family first, robotics, and Sampi. And I also do a lot of sailing and things like that. But the biggest one is my whole life has always been around composites. So I really enjoy making parts and things like that for that. The agenda for today, I'm going to talk a little bit about who CAG is, what we do, and why we do it, and give you guys a couple of case studies and how we approach things. And then we'll kind of go through the conclusions of what we've done. There's a big debate between IACMI and CAG about who came up with the 3 C's first. We're not quite sure, but if you look at the way we do it, we pretty much follow on to what the IACMI does. So our key terms are connect, collaborate, commercialize, and so that kind of flows with the TRL levels that IACMI has, and we kind of continue on is what we talk about. So CAG is a consortium of lots of different companies, public institutes, public and private companies, and academia. We collaborate with these companies to develop solutions for our OEM clients, and pretty much that's what we do. We have several retained OEM clients, and we find technology solutions for those OEM clients to develop, most of the time, composite solutions for them. And the biggest thing that we're really focused on is commercialization. So we do seek out OEM clients that are disruptive in their markets. Most of the times, the companies that we've worked with have not had experience in composite materials, and so they're new to the markets for composite materials. What we also do is we've got our partnerships that you'll see are very strong and a robust composite supply chain. So we represent all the different materials and that need to go into, and the manufacturing methods, everything like that need to happen for these to OEMs to solve their problems. We pretty much have, we also go after innovative new technologies to bring those to the table for our OEM clients. One of the key things that we do is if you look at our OEM clients and our partners, there's non-competing. So we don't have one glass supplier, one resin supplier, and if you look at the OEM clients, the same way. And because of the way we approach things, we move concepts to commercializations really fast. So this represents some of the OEM clients that we have. Our main two that we work with are Wabash and Trinity. Both of those we're retained by. The other ones are companies that we've worked with in the past and continue to develop products for, but we're not necessarily retained by them. The other thing we do is we work closely with academic and agencies like IACMI. We have an office at the Checkerboard facility and also lease space at the new Innovation South. We've also worked with several creatives with Oak Ridge, and we've done a lot of work with Dr. Uday Vaida and Dr. Panamani at University of Tennessee on different projects. And then we also have done projects with NASA, Department of Transportation, and DOE. So this is kind of a busy slide, but it does represent all the partnerships that we that are all our OEM, all our members that are part of our organization. As you can see, we kind of do represent the supply chains. You got the Vector Ply as fiber as a fiberglass supplier. We got ExxonMobil as a resin supplier, NCS, and then we got manufacturers like McLaren, ECC Corrosion, Structural Composites, to name a few of them. But we also bring into the port like the manufacturing equipment suppliers like MVP, Briskey, Luna, SmartTech, and all these companies. And then we also bring to the table Manifest Engineering and other engineering firms like HLA engineers to help make sure that we can do the FEA and modeling. So really, when we work with our companies, we're OEM clients, we're bringing the whole picture of development force to them. So one of the things we do too is we work closely with our OEM clients to understand their needs, and then we help them find technologies that meet their needs and help them develop solutions. And one of the ways we have doing that is working closely with like the Oak Ridge Innovation Crossroads Group and the University of Tennessee's Research Foundation. This helps us look at new companies that are coming down the pipe that have really interesting technologies. And then we some of the companies that came out of like the Innovation Crossroads companies, Endeavor Composites, Perseus, Shift Thermal, Thermoverse, these companies have come out of that industry. And we also have a couple other companies that are new startup companies that have really interesting technologies like Rock Fiber, Green Tech Solutions, a recycling company, Eli, Manifest Engineering. These guys are all startup companies that bring some very interesting technologies and services to our OEM clients. With that, we also go after, a lot of these companies have gotten funding through our OEM clients to look at new technologies and get them an opportunity to get at the beginning of their startup to have funded research projects from potential OEM clients. And we also work, these are companies that we've chosen to work with because they have a technology that we think we can commercialize at our OEM clients. So what's our process? We're really deeply embedded in our OEM clients. We work monthly meetings, sometimes even closer to bi-weekly meetings with these guys, and look at their how to solve their problems and what they're looking for. We're very nimble because of the way our organization is structured. We can be a one-man team, or we can bring 300, 400 people to play in this, because we can move pretty quickly and really move things from concept to commercialization really fast. We are really focused on cost competitive, because a lot of the industries that we're in like the trucking industry, they're very cost sensitive. So we really focused on bringing solutions to the table that are cost effective. We also go after kind of more of a hybrid approach. Composites don't solve everything. We look at it, okay, what metal structures, what other type of materials can we bring to the table and solve the problems for our OEM clients. This is kind of one of the big companies we work with is Trinity Rail, and I'm not going to read this one, but Ken Huck was the senior engineer that we were working with, and they had they really appreciated the work we do, and we have several programs going down the pipe with them right now. So kind of kind of a quick one on our approach. One of our first major projects was the Wabash National, the composite trailer. Probably a lot of you guys have seen this slide before, but really wanted to highlight what we did. Wabash came to us and said, hey, we want to make trailers, composite trailers. We found a solution with the Prisma technology of structural composites. We brought in the supply chain and equipment suppliers to solve the problem. We even brought in a recycling company to look at how they're going to do the end of life and manufacturing issues. So this is what we do. We find, okay, we see an issue and we bring a team together to solve their issue. The market was a market disruption. That was the key to it. We got, significant thermal improvement, significantly light. It was a lot lighter. And these we continue to improve. We're at like 30% thermal improvement and 25% lighter right now. Again, the thing was that, started concept to commercialization was 3 years. We commercialized in 2016 and have continued to improve their project with some of the work that we're doing with them now. Another project we talked about is Trinity Rail. Part of the reason I wanted to kind of show this slide is it's the same approach. We basically work with a company. Trinity said, hey, we want to work on we see you guys are working in Wabash. We think this is an industry that would work well, technology that would work with ours. And what you'll see is these two companies are not in the same place. So these basically have their own, and this is how we work too, working with our OEM clients, is we work with only one area of the client. Trinity Rail does rail cars, these guys do trucking. So they're not a competitor. One of the interesting things here is you see that Wabash is on the outside. So one of the things that we did with Wabash is help them set up a manufacturing plant up in Minnesota. So what they're doing right now, we leveraged their technology and brought it to the rail industry. And then now they actually are fabricating parts for the Trinity Rail program. So this is the 70-foot rigid reefer car that we built. This is the trailer, the design of the thing. It's got two composite sections on the top, and then it's got the steel structure underneath. One of the things I want to highlight here is one of the biggest things we'll see it on the next slide, is that we'd reduced the number of parts from 2,000 to 150. And that's really all the design of the steel structure underneath. And that they limited a lot of the supports underneath that structure. And we helped them do that design work and work closely with Trinity to help do that design. Again, we went from reduced the flooring section of the thing by 4,500 pounds per trailer, 200 to 150. So it was also one of the things that is interesting is it doesn't look anything different. There are aluminum face sheets on the top of it, mostly because they use that for transferring their heat back and forth. So it is, but that also is we fabricated directly on that aluminum plate. So this is an assembled structure on top of the aluminum plate. Again, another 2021 Camex window. So really, again, CHE is really about commercialization. That's been our goal, to help commercialize composite structures in there. One of the ways we do it is bring funding from our OEM clients to our companies that belong to us. So over the last 10 years, we brought about $13 million worth of funding to our partnership through us. We've gotten significant amount of. The other thing I'd like to point out in this slide is the job creations, significant amount of job creations. And the other thing is we've brought over $310 million worth of new composites. And I would point that out. It's new composites because the industries that we're working in had not had composites in it. There wasn't very little truck composites in the trucking industry and commercialization. Same thing in the Trinity Rail and the rail car, really limited amount of commercialization success in using composites in those industries. So $310,000 in new work in new industries for composites. Just kind of the TRL 7 to 9 track record, where we've been commercializing products for over the last 13 years that we've been involved with composite application group. We've got we're looking at a new composite part for Trinity. We're going after another IACMI award this next year or next year. And then we've got a couple other new OEM clients that we're talking to that we think we're going to land this year. So we're pretty excited about that because it's going to be in a different industry, again, that hasn't had a huge amount of success with the composites. So we're continuing down that pipe. Again, the 3 C's, we connect all our partners with our OEM clients to really go after and make sure we work together to collaborate to help to develop new products for our disruptive OEM clients. And then we commercialize. And that's the key to what we do is we really focus on commercialization. That's my my story, our story. Jeff McKay was the founder of the company 13 years ago, and I came on board about 4 years with these guys, and have been thrilled to death to be with them the last 4 years. Any questions?
Thanks, John. Yeah, I don't see questions out there. I'm sure, for a lot of people here, this may be their first introduction to Composite Applications Group, and useful to note that we work very closely with you guys.
Yep.
A lot of your members are our members, and vice versa, and we're able to leverage a lot of obviously university and large scale molding equipment to get things to a certain point, which we can hand it off to you guys to to take it to the next level.
Agree. And that's part of it. We work closely with both Oak Ridge, IACMI, and University of Tennessee, since we're out of Knoxville, Tennessee area.
Right.
Okay. Thank you.
What do you think? What do you think the next big challenge is, though?
I think infrastructure is an area that we've had there's some big needs to it. And I think that's one of the areas that we're going to be doing some focus on, hence why I'm part of the IACMI infrastructure and construction group. Construction is another area that we think are an areas that we're challenging that I think will meet a lot of needs, especially with and I think one of the things that we talked a little about in infrastructure and construction group, and I think we're going to have a presentation on that too, resiliency of and that composites just offer so much in the infrastructure world because we're long lasting, and that the resilience and being able to withstand things like fires and things like that are very beneficial.
Yep. Yeah, and we did have a great resource pool project on the fireproof building panels that I think has drawn some attention, and looking forward to.
And again, I reiterate that our approach is, and I think everybody's approach is, composites don't solve everything. They're a tool. That's one of the tools in our toolbox is that we work closely with metal suppliers and companies like that. And that's always going to be the case. And I think that's everybody needs to kind of look at it as that as a hybrid approach.
Okay, good. All right, so See, Kim, David Jack is is joined as a panelist. David, we'll put you on the spot. Is there something you'd like to say, and maybe in particular promote? We have a few minutes left here if you want to promote ACCE.
Well, yeah, no, thank you very much. Actually, very, very impressive talks. I thoroughly enjoyed those, both of them, just seeing the different applications. As a guy who drives a Corvette, always love hearing about the adhesives on those. But really want to, just encourage folks who are interested. The Automotive Composites Conference and Exhibition is coming up. This upcoming September, first week up in Novi. We're just starting to arrange some of the keynote speakers right now. The paper portal's open. Actually recruiting speakers. We're very blessed this year. We have Hendrik from Volkswagen, who's one of our technical program chairs, and so is Dominic from Simitens, who's the other technical program chair. Mike Schwajek is the conference co-chair, along with myself from Tasian, and looking forward to seeing this year. It's the 25th anniversary of ACCE, and hoping to have kind of a look back and a look to the future.
Yeah, that'll be the first week of September. So the first, it's the
That is correct, sir.
Wednesday,
It is
Thursday, and
September,
Friday after Labor Day.
Yeah, September 3rd through 5th.
Yeah, in Novi, Michigan.
In Novi, Michigan. That is correct, sir.
Yeah, I'm proud to be able to say I've attended every single one of those conferences since it began in 2001.
Yeah, I've got a few more to go. I think I'm on number 15 right now. Make it a point every year. My students absolutely love it. I think one of the things that they enjoy the most is making the contacts. Every year, one or two students comes back with the individual who ends up being their future employer. So great way for my students to make connections, but really just enjoy seeing the way the industry are able to make connections with each other.
All right. Well, thanks, David, and encourage folks, if they've got something to present that's in the automotive space and composites that you think, that includes bonding, joining, finishing, recycling, natural materials, 3D printing, to SMC, thermoplastics, thermosets, lots of categories and lots of opportunity, whether it's electric vehicles or hybrid vehicles or good old combustion engines. If you got something that you think can help the industry, please plan on presenting a paper or showing up and sponsoring a booth. Lots of opportunities there. So with that, I will close out today's episode of Innovation Insights, and we will see you in March. Hopefully we'll see a number of you at ACCE. At JEC, at JEC next month in Paris. So until then, have a good rest of your week and rest of the month. Thank you.